Hello, I'm Pablo Sepulveda, and I will be co-presenting this study with Max Marschall, a work we did with Kexin from Melbourne Uni. This is the story of how we apply the EnerPHit methodology to be able to articulate an advice to Melbourne Uni as a client. So the presentation had four parts: an introduction to tell you a little bit about the original scope and the methodology we proposed to Melbourne Uni, the proposed strategies and the result and the conclusions of the study. So the introduction and how we get to propose to Melbourne Uni this methodology and the importance of this building for the university. The old engineering building is one of the most emblematic and oldest buildings in Parkville, so a source of pride for Melbourne Uni. So you can see here a collection of photos we took that are showing a little bit of the nice architectural features of this building. Very high ceiling heights, skylights, chimneys, double brick, and very generous and well-designed spaces. In this slide, you can see that the building had a lot of add-ons through almost 50 years. It have been adding more and more spaces. But what is quite nice is that the connections and the architectural character have been preserved, and you can really see the unit of the architectural language in these different stages of construction. When we started the project, we counted on getting access to the energy consumption data from the building. We did have access to it and a breakdown, but it was very clear for us that that was not very exploitable for what we wanted. The energy consumption of the whole building was overall very, very low, 50 kilowatt hour per square meter per annum, approximately. So we started asking some questions, and we realized that part of the building were not used. So it was very difficult really to understand how the building worked and how really is used. So we didn't have like a lot of time to do a very thorough investigation about how the building was used. We noticed that the lighting seemed too high, and when it's too high like that, that have consequences that increase the need of cooling and really reduce the amount of heating. So we were not expecting a result like this, and we realized that we were not able to exploit this data. So we decide to apply and propose another methodology. So the original scope was really taking this data and making sense of it, which was very difficult. So we kept the intent that future-proof this building and make it more energy efficient and more comfortable. But we changed the approach. The approach was really focused into the services, upgrading the services, and we focus in upgrading the building fabric. So really get into the demand and not in the efficiency of the system. So have a very focus in passive design and not the active system efficiency performance. So we talked with the university and we changed the methodology, and we brought this methodology of EnerPHit and using modeling to get things done and to guide them into what they should be doing. So as we changed the approach and the methodology for this building, and we really focus in the passive design and building fabric performance, we really wanted to understand what was the original passive design features of the building. The building was naturally ventilated, so you can see that all the spaces can be naturally ventilated. there is a decent amount of natural daylight and a lot of thermal mass. So we wanted to exploit and to understand what was the original wisdom of the building. There were some things that also we thought that were interesting. The chimneys, of course, not for using it in terms of heating. We started like brainstorming what that old system can be reused. So we want to really to address the source of the problem. So really get the energy demand very low, and really take advantage of all the good things and the good features of the building itself. Also, what we realize is not always improving the energy performance mean and equal to improve the comfort. So also it was an investigation about that, and we did a parametric assessment with the EnerPHit methodology to understand what were the right combinations to make and think really holistically.
So we use two different software platforms in order to conduct our simulations. The first set of simulations related to the comfort assessment, and the second set to the energy consumption as it related to the performance, the thermal performance of the envelope. In both of these cases, you need a 3D modeling platform to generate the geometry, and then we use a plugin in order to access building performance modeling software that runs under the hood. So for the comfort simulations, we used Rhino 3D to generate the geometry. And then there's a plugin, Honeybee, that allows you to use it as an interface to Energy Plus, and we use this to conduct these comfort simulations. In the case of energy simulations, we decided to use the PHPP spreadsheet. And here we used a different modeling platform to create the geometry, namely SketchUp. SketchUp has this Design PH plugin that allows you to access PHPP. So how do you go about evaluating these different design options? Well, we chose 3 different criteria. The first one relates to operational energy consumption. The second relates to comfort autonomy, and that is a metric where basically you simulate the building without HVAC systems and assess to what extent it is naturally comfortable. So in case the HVAC system breaks down, is the building resilient enough in order to provide sufficiently comfortable conditions? The third metric here was related to cost. We suggested several passive strategies, in this case 4. The first one was cavity insulation. Then we proposed several air tightness measures, double glazing, and finally a natural ventilation concept. And we also analyzed combinations of these, as you're going to see in a minute. So the first strategy was cavity insulation, which is pretty straightforward. So currently we have a double brick construction with a cavity, an air cavity in between. So the idea is simply to extract some of the bricks on that outer brick layer and then to insert some insulation material on the inside in order to reduce the heat transmission, or in other words, reduce the U value through the wall. The nice thing about this strategy is that in terms of heritage considerations, it is possible to conduct it in such a way that aesthetically you won't see that there have been works done on the outer facade. You extract some of the bricks on the outside and use those same bricks to be reinserted. You can even basically collect the mortar that you extract while removing the brick and remix that mortar in order to reduce the visibleness of the works. The second strategy was a set of air tightness measures, and these are quite there are quite a few different things that you can do in order to increase the air tightness. For one thing, there are some clear penetrations through the existing walls in forms of vents and windows that don't shut properly. Obviously, that would need to be renovated and sealed. Then there are also, in cases where there are penetrations through walls, for instance, through pipes or light fixtures, to basically fill the gap in between the element and the wall. And then there are more extensive measures like applying a spray film to the inside surfaces, or also just using sticking joints and weather stripping and draft excluders for the different elements like windows and doors.
The third strategy we proposed was changing the double glazing. Of course, that had some implications in terms of heritage. We are aware. So there are some companies that are able to perform this quite nicely. We have the intuition that this can have a very good outcomes in terms of comfort. So we were very keen into exploring this one. The fourth strategy was related to natural ventilation. We knew that this building was naturally ventilated originally, and you can see all the plants, and you can see the pattern of cross ventilation and how the building was able to purge the excess of heat with this feature. So one of the things that we start looking at is like really choosing what kind of windows could really take into consideration safety, so not being reachable by the student, and seeing where we could situate the different openings to create a stack effect and do it more efficiently. One of the things that we thought that was very interesting was using the skylights, because you can create more this thermal chimney effect. And we flirted with this idea of using the old chimneys that now they are not in use to create this cooling system with the old chimneys. So we thought that that could be very cool. So we did some testing, and we realized that you can have a performance multiplied by 4 if you compare with the same area of opening, if you do it with the chimneys and with the skylight by 2. So moving to the results. So what you see here is each of the strategies that we propose, and is the individual result. So is we leave everything the same, and we just change one of the proposed strategies and see what is the effect. So you can see the heating demand, the heating peak, the cooling demand, and the cooling peak. We have the base case, how much is consuming, and then the reduction of consumption and the proportion of the energy that is needed in relation to the base case. So the individual result, again, but this time we are presenting the energy, comfort, and cost. In energy, the energy demand and the peak loads, and in the same way in relation to the base case and the reduction of the energy demand. So what you can see, what is interesting to see, is that the air tightness is the only one that do not improve in the cooling demand, improve in the heating demand. Then in terms of comfort, the natural ventilation was the most effective. Second, the change of double glazing. In terms of cost, natural ventilation is the less expensive, and the double glazing is the most expensive one. We did a very broad iteration between the different combination of the strategies we propose. This is what we present to the client. Natural ventilation was always proposed as was the most cost effective, and in terms of comfort, the best one and cheaper. So this is the result with the combination that we propose to the client. Natural ventilation, as I said, is always there, insulating the walls. Combined with natural ventilation is very, very powerful combination. And then we have, of course, an increase of the performance in terms of energy comfort with the other strategies that we propose. So these are the same scenarios proposed, but this time we add an HRV with 75% of energy heat recovery performance and air tightness of 1 ACH. In the other scenarios, we propose a 4 ACH because we thought that it was easy achievable for the project. And the result here is for the heating demand, and you see the decrease of needs and demand of the building with the different scenarios, and adding the additional scenario with the HRV and the air tightness with EnerPHit level. These are the same iterations that I mentioned, but this time with the cooling demand. What is interesting to see is when, as soon as you add air tightness, the cooling demand start increasing. Have to compensate it maybe with more natural ventilation to purge it, and yeah, all the different scenarios they put there increase the performance, but the air tightness have to be really taken into account with natural ventilation to overcome that decrease of performance. So this is a metric we presented to the client to facilitate their decision making. Blue represent improvement of the performance, and red a decrease of the performance or an increase of the cost. So we have on the right side the total cost that is increasing with the different iteration when you add up the different strategies, and in blue is really the increase in the percentage of improvement with the different strategies we propose. So this metric is showing the individual cases, the individual strategies, and the proposed combination of the strategies.
So just to summarize, these were the three scenarios that we presented. In all three cases, we decided to incorporate natural ventilation simply because we found that through a relatively low upfront investment, we could see a very beneficial impact, and also because natural ventilation is a good complementary strategy towards the others. As a first additional strategy, we decided to incorporate cavity insulation simply because we found that, again, through a low upfront investment, we could see a very positive effect on building performance. As a second measure, we added the air tightness measures and then the double glazing. Now, in terms of the reduction in energy consumption, we could see a very positive impact already in scenario 1 by 64% reduction, and then we could incrementally increase that by using the other strategies. In terms of comfort autonomy, the second scenario didn't add much benefit, but the third one, so adding the double glazing, we saw quite a substantial increase. But this is also accompanied by a very substantial upfront investment, and opting for this option would just need to be seen as a trade-off between upfront cost and building performance. Now, what we presented today was really just an early design initial investigation, and this would have to be accompanied by much more rigorous analysis and site visits. We have a set of historic plans that would need to be investigated and coupled with some on-site surveys. For instance, there is this cavity camera survey equipment that we would need to really investigate what the current construction looks like and to what extent the cavity insulation is feasible. We have begun with some very initial heat flow simulations, which you can see here is a section through the exterior wall with a floor slab that's piercing the outside wall. At the on the top, we have what we think is the current situation without cavity insulation, and below we've added the cavity insulation. Now, for instance, here we're unsure as to where the slab ends. Currently, we've assumed it to pierce the inside layer of brick and be flush with the outside layer, but that would have to be investigated. What that causes, of course, is a bit of a thermal bridge. It doesn't impact the general performance too much, but it would be something that would have considered. And so this is why we've created a bit of a timeline for the Melbourne University moving forward, which would start with our on-site surveys and some more accurate 3D modeling, just to get the massing right. That would be followed by the tendering process and an updated cost plan. Then on the basis of that, we could run more in-depth simulations, both in terms of building performance simulation, but also CFD simulation, since we've proposed a relatively unique natural ventilation scheme with some potentially more advanced control algorithms. This is something that would just need to be assessed and tested.
We are ending our presentation of the study for this building, and we wanted to share with you some of the internal reflection we have with the Integrated Design Lab with you. So if you see the bigger picture, you realize that we are today able, and this is very broad calculation, but you can do it at home if you want. We are building around 1% of new buildings per annum. And if you imagine that this 1% is a passive house standard, let's say, or an average of a very good high performance building that is able to consume 5 times less energy than a classic building, this is a very marginal improvement. So the energy demand of this new stock only represents 0.2% of the ongoing needs for energy demand of buildings. This is not fast enough. This is not enough. We cannot really rely on changing the stock and making it the new stock more performant only to stop the climate crisis we are living. So the importance of retrofitting is for us quite evident. We have all this old stock that can improve have the potential, as we show in this study, to improve their energy needs in a very dramatic way. So it's a huge potential to tackle the energy demand, energy emissions, energy resources, all of sort of impact that building has over our environment. So if you also add the embodied emissions of the materials and all the impact of extracting raw material from the environment, it has the impact is even bigger. So we can say that retrofitting can be a very big part of the solution. I'm an architect and I love new buildings, but also I love old buildings that have this wisdom that is we can unlock and we can restore and retrofit with passive house techniques. So this is something that this is a reflection we wanted to share with you.
So anyway, this was our presentation. I really hope you enjoyed it and it was informative. We are pretty excited moving forward with this project because we think it's really unique and a great opportunity for us, and also unique in terms of being able to use passive house thinking for a heritage listed existing building. So we're really excited about this, and yeah, thanks for listening.